So far we've been talking about, a couple of tools that we're going to be utilizing for basically analyzing these second order types of systems. And the last thing that we talked about was the Laplace transform itself, and also we talked a little bit about the initial conditions and the timeline. But let's just go ahead and continue going through the actual tools that we're going to be utilizing in order to get to where we can just solve these problems and work through examples. So this is a continuation of the section that I really want the class to be able to work automatically through almost. So again, I think the most conceptual parts of circuits 2, at least for this type of dynamic system analysis, is really working through basically the initial conditions as well as the derivation of the differential equations themselves for either series or parallel networks. But once you've actually derived that differential equation, the operations from then on are not really as conceptual based. Basically, it's more of a skill set. And understand there's a difference between actual concept-oriented type of analysis where you're applying concepts. In this case, we're applying KVL, KCL, as well as the current voltage characteristics of each element, and being able to relate each to the other. So in this case, we're actually working with the skill set. Now with these skill sets of taking the Laplace transform of the differential equation as well as being able to perform the inverse Laplace transform based off the type of system that each are, or basically the roots of the system, that should be something that you guys practice over and over and over and over and over again. Don't just do a problem or work through a Laplace transform and its inverse just one time and say that you got it. Work it to where you're doing it very, very efficiently and not having to use any reference whatsoever. That's basically how we actually get more efficient with this type of analysis, to be able to work the skill sets and be able to basically do those very, very quickly and efficiently. So there are 3 different types of responses that we're going to be working within this class. The first is what we say is overdamped, and that's basically when we have real and repeated roots for basically the differential equation. Now, when we actually have, whoa, I just said something wrong, just real roots, sorry. Critically damped is actually when we have real and repeated roots, okay? So basically when those roots are actually repeated, how do we actually analyze that system and actually perform basically what we call the partial fraction expansion. With underdamped, that means we actually have complex roots. When we have complex roots, that's when we actually start seeing the oscillation happen within that exponential form of the response. Another way of going back and thinking about damping is essentially how much resistance is actually preventing the system from actually gaining oscillation within its response. So with overdamped, that means we have no oscillation whatsoever. It's a very, very stable type of system. Critically damped, another way of actually saying that is the threshold damping. Basically, the amount of resistance that is within that system, where it's just right at that point where it's about ready to go into a form of exponential oscillation or rise, exponential rise or decay with oscillation within it. Now, basically, once we get into underdamped with those complex roots, it means that the system doesn't have enough resistance whatsoever. A good analogy for this from a mechanical standpoint was if you have basically a rotating arm, robotic arm, and there's not enough counterweight behind the system. And all of a sudden it starts to move, and then all of a sudden we start seeing a vibration that actually happens. And we all know that with a mechanical system, having vibration within that rotational type of movement is not good whatsoever. So how we actually deal with the differential equation once we've actually gained the form of Vs or Is, well, in order to actually solve for the system and get it back into the time domain. Remember that the Laplace transform, we put everything into the frequency domain so that we can actually solve the system easily and then gain the total response back in the time domain. Well, the way that we actually have to do that is through what we call partial fraction decomposition. And there's a very, very specific way that we actually have to use it with real roots for the overdamped case, repeated roots for the critically damped case, and also for complex roots in which we actually have oscillation within the system. So, just based off the forms of these, x, y, and z here in the numerator, that can be anything. That can be a partial function of s, it could be a real number, but in order to actually take the inverse Laplace transform of these forms when we have something in that numerator, we can't actually just go ahead and take an inverse Laplace transform in which the denominator has basically each pole or root in it. So we actually have to decompose each of these functions into simple terms in which we can actually take that inverse Laplace transform. And so in this case, for f of s, this would be for an overdamped case. Here we have x over s plus 1, s plus 2, and times s plus 3. We decompose that into a variable, or basically a coefficient of a over s plus 1 plus b over s plus 2 plus c over s plus 3. And I said variable because these three in the numerator, a, b, and c, those are actually going to end up being the eventual coefficients. But we have to actually find the values of a, b, and c, and that's what we're actually going to show through the sample. Now with g of s is equal to y over s plus 1 squared, that is a repeated root of p1. And so in order to actually decompose that into its simple terms, we have a over s plus 1 plus b over s plus p1 squared. We actually have to include this form right here for the repeated root. Otherwise, we're going to have a problem finding this value for b. So we have to include a over s plus 1 in addition to b over s plus 1 squared. Now, h of s here, this is for anything that we have a complex root, basically polynomial equation in the denominator. That gets decomposed into a over s plus alpha over s plus alpha squared plus beta squared. This in the denominator is what we call that equation's completed square. And we're going to get back to that in an example in which we're actually going to show how to perform this in order to get the forms of alpha and beta squared themselves. And then plus a squared over beta over s plus alpha squared plus beta squared. So the actual inverse Laplace transforms of basically a real root, a over s plus p1, is equal to a times the exponential e to the negative p1 times t. For the inverse Laplace transform of a repeated root, here we have a over s plus p1 squared. That equals to a times t. We multiply that by time times the exponential of negative p1 times t. Now, as far as the form of the inverse Laplace transform, it's quite long, and I kind of ran out of space right here, but we're going to come back to that in the last example that we're going to show, in which we're actually going to see two forms in which we have basically an exponential multiplied by a cosine and also an exponential multiplied by a sine. So we're going to get back to that. But let's actually go through the process that we're going to utilize in order to decompose the form of v of s or I of s and then actually find the coefficients a, b, and c. So we're going to look through each case, an overdamped case with real roots, a critically damped case with a repeated root, as well as the underdamped case with complex roots. All right, let's take a look. We're going to be doing a lot of maneuvering today. All right, so this is going to be an example that we can utilize for the inverse Laplace transform, in which we have an overdamped case and real and repeated roots. Here, the root for f of s, we got f of s is equal to s squared plus 12 over s plus 2 times s plus 3. Now, the root of s is equal to 0. The root of s plus 2 is negative 2. The root of s plus 3 is equal to negative 3. So we're going to actually go through and derive basically these forms here. So here we have s squared plus 12 over s plus 2 times s plus 3. So we're going to decompose this into the three forms in which we have a over s plus b over s plus 2 plus c over s plus 3. Now these three are now in their simple term forms, in which we can find a plus b plus c, but we have to, in order to find a, b, and c, we have to set up basically a system of equations, and it's very, very easy to do this. Now, my method of actually finding a, b, and c may differ a little bit from what you may have seen in your differential equations class. I don't care if you utilize my method or another method, as long as the values a, b, and c are the same. So in this class, I'm going to be using a very specific method. It's just what I like to use. If you want to use a different method, that is totally fine. I have no worries with that, as long as a, b, and c are correct. So here I take the denominator of s times s plus 2 times s plus 3, and I multiply both sides by the denominator, in which we get s squared plus 12. That's equal to a over s times s plus 2 times s plus 3. Here, the two s's would actually cancel each other out, plus b over s plus 2 times s plus 2 plus s plus 3. S plus 2 cancels out, and then c over s plus 3 times s plus 2 times s plus 3, where s plus 3 cancels each other out. So now what we actually have is an equation that we could possibly evaluate in order to come up with basically the three unknowns that we actually have of being a, b, and c. So s squared plus 12 plus a times s plus 2 times s plus 3 plus b times s plus 3, and then c times s plus 2. Now, how you develop this system of equations, we got to develop three equations because we have three unknowns. And once we get those three equations, we can just basically put them into our matrix, augmented matrix of a and b, and perform row reduction in order to get it into its echelon form, so we get the solution of a, b, and c. So the way I actually do this is I evaluate this equation 3 times, in which I allow the complex variable of s to equal 0, s to equal 1, and then s to equal 2. Once we do that, we actually get three equations and three unknowns of the form of 12 is equal to 6a plus 0b plus 0c. 3 is equal to 12a plus 4b plus 3c. And then finally, 16 is equal to 20a plus 10b plus 8c. I put those into an augmented matrix, and I row reduce them to the echelon form, in which we gain a is equal to 2, b is equal to -8, and c is equal to 7. So these are the coefficients that we can actually utilize in order to complete basically the form of that partial fraction expansion into the simple terms for basically f of s. So what I'm showing is a 100% equivalence here. S squared plus 12 over s plus 2 times s plus 3 is actually, once we go through and expand that into its simple terms, then the equivalence of those expanded simple terms is 2 over s, and that's equal to, minus 8 over s plus 2 plus 7 over s plus 3. So when we take the inverse Laplace transform of each of these, the inverse Laplace transform of 2 over s is equal to 2. The inverse Laplace transform of -8 over s plus 2 is -8 times e to the -2t. And then 7 over s plus 3 is just going to be equal to 7 times e to -3t for its inverse Laplace. So the whole entire solution for this second order system is 2 minus 8 times e to the -2t plus 7 times e to the -3t. And if we really think about what's going on here, this portion, the exponential portion, is our transient phase, okay, that transient phase. And here, this is our final solution, whatever this type of system was, whether this was IS or VS, 2 represents this final steady state solution for whatever, this could be the voltage across the capacitor or the current through the inductor. But we see here that once we actually take the inverse Laplace transform, we do come out with what we would expect to see in terms of basically a total response that represents the transient portion as well as the steady state as the system moves towards a time period of t is equal to infinity. So that's an overdamped case. Let's continue on with our discussion. Let's look at the critically damped case. All right. All right, with the critically damped case, we're actually going to consider basically a system in which we have a repeated root. Now, this is not necessarily normally a system that we would directly have, but it shows a good example of how to actually analyze the system appropriately. So, in this case, V of s is equal to 10s squared plus 4 over s times s plus 1 times s plus 2 squared. So here we can actually perform partial fraction expansion, go ahead and put it and expand it into its simple terms. So a over s plus b over s plus 1 plus c over s plus 2. Remember that, we have to include the s plus 2 in the denominator, as well as the actual term of d over s plus 2 squared. So here we perform the same type of method in order to set up basically that system of equations. In this case, we have A, B, C, D. We need 4 system equations in order to find A, B, and C. So once again, multiply both sides by the denominator of s times s plus 1 times s plus 2 squared. And then we get the final, we get the form of an equation of 10s squared plus 4 equals a times s plus, that was supposed to be s plus 1 right there. Ooh, man, forgot that. So s plus 1 times s plus 2 squared. And then we get plus b times s plus 2 squared plus c times s plus 1 times s plus 2. And then finally plus d times s plus 1. And then once again I go through with basically this form here, I evaluate that complex variable at 0, 1, 2, and 3. That gives us 4 equations, 4 unknowns. Our unknowns obviously are A, B, C, D. So once again, we put them into a matrix, we perform row reduction, and we get the values here of A is equal to 1, B is equal to negative 14, C is equal to 13, and D is equal to 22. So the equivalence of V of s from this form, this initial form that we solved for, of 10s squared plus 4 over s plus 1 squared times s plus 2 squared, that comes out to be equal to V of s is equal to negative to 1 over s minus 14 over s plus 1 plus 13 over s plus 2 plus 22 over s plus 2 squared. And when we take the inverse Laplace transform of V of s, we get V of t is now back into the time domain, in which we have 1 minus 14 times e to the negative t plus 13 times e to the negative 2t, but right here plus 22t times e to the negative 2t. So this is a good example of how we can actually solve critically damped systems and actually get it back into the time domain. But as you can see, between overdamped and critically damped, the process is very, very similar. We perform the partial fraction expansion to get basically the form of V of s or I of s into its simple expanded terms, so that we can actually have a term that we can take the inverse Laplace transform of. But all we have to do is basically multiply through both sides, get an equation in which we can actually evaluate it into basically our unknowns, and then we actually put it into our matrix so we can actually get those coefficients developed very, very efficiently. So very, very similar process. It's just how we actually expand it. Now, with working with an underdamped case, we're actually going to have to complete the square in order to get the equation into basically get those terms into something that we can actually take the inverse Laplace transform. And I actually find this portion to be very, very, very interesting because of how those roots actually relate not only to the rate of the exponential, but also to how it relates to the frequency that that system will oscillate at. So let's take a look at that. Kind of maneuvering all around the room today. Okay. All right. Inverse Laplace transform for an underdamped case, meaning that the roots are complex, so we're going to see oscillation within that system. So here, I'm going to say that I of s is going to be equal to 18 over s squared plus 18s plus 100. This, in the case, we can't factor that. That characteristic equation, essentially, we can't factor that. And so what we're going to have to do is complete the square to get it into such a form that we're going to be able to get alpha as well as beta squared. So again, I of s, if it's equal to 18s over s squared plus 18s plus 100, the partial fraction expansion of that, this is actually given within the book that went ahead and did a very, very good job of that for us, is this actually equals the form of that partial fraction expansion in which we have a times s plus alpha over s plus alpha squared plus beta squared plus b times beta over s plus alpha squared plus beta squared. So we have to actually complete the square of s squared plus 18s plus 100 to put it into this form here of s plus alpha squared plus beta squared. So we actually have to complete the square to give an equivalence that's going to render us the values of alpha and then beta squared. Once we get those forms, basically we start performing the same, type of matrix development. So, in order to complete the square, it's quite simple. All we do is take 18s here, we're going to take the coefficient of 18, we're going to divide that by 2 and then square it. Okay? So take 18, divide that by 2, square it, but since we're adding in a term here, we're going to actually have to subtract that off in order to provide that equivalence. Remember, this is completing the square is a manipulation of the equation into a different form. It's the same equation, it's just manipulated into a different form. And so whatever we add on, we have to take off. So once we actually add in the form 18 over 2 squared, that gives us basically a form here of s squared plus 18s plus 81. And then that right here, we can actually factor that into s plus 9 squared. But when we take off 18 over 2 squared and add that to 100, we get the value of 19. So right here, we actually have the values of alpha and beta squared. So alpha, in fact, is actually equal to 9. Beta squared is equal to 19. But the interesting thing here, guys, is that beta, not beta squared, but just beta, which is equal to 4.3589. That's the square root of 19. Beta is actually going to be the angular frequency measured in radians per second that we would actually see for that oscillation that we actually put into our exponential decay or rise. So now we actually have the forms of alpha and beta squared. So now we can apply that to the partial fraction expansion when we have a complex root. And once we get that, everything afterwards is basically the same. So let's take a look. I of s is equal to 18s over s squared plus 18s plus 100. That comes out to be equal to a times s plus 9 over s plus 9 squared plus 19 times b times 4.3589 over s plus 9 squared plus 19. So from here, same thing as we've done with the overdamped case and the critically damped case. We multiply both sides by s squared plus 18s plus 100. That takes out our numerators on either side. Now remember, you may say, well, s squared plus 18s plus 100, how does that cancel out s plus 9 squared plus 19? Remember, s plus 9 squared plus 19 is the completed square version of s squared plus 18 plus 100, 18s plus 100. So they do cancel each other out. It's the same equation, just in different forms. So all we're left here is 18s, and that's equal to a times s plus 9 plus b times 4.359. Two equations, two unknowns that we have to develop. So s is equal to 0, s is equal to 1. We evaluate those two equations, in which we actually get a is equal to 18 and b is equal to negative 37.2. So we go ahead and apply those to our partial fraction expansion of the original function of I of s. So here we get 18 times s plus 9 over s squared plus 9 squared plus 19. And then minus 37.2 times the square root of 19 over s plus 9 squared plus 19. Note here that I did not multiply negative 37.2 over the square root of negative 19. I did not do that because this is the form that we will take the inverse Laplace transform of, in which basically that square root of 19, that coefficient of that term, has to be left alone, because negative 37.2 is the coefficient, not negative 37.2 times square root of 19. We leave that alone. Okay, don't do that. Do not multiply those two together, because when you take the inverse Laplace transform, number one, that's going to be incorrect. And number two, I would have to count off for that on your exam. So let's not do that. Keep that in mind. This is the reason why I say practice these over and over and over and over again. Just do the same thing over and over. Do it 5 times in a row, just to make sure that you have automatic on that. You're not going to make that mistake on a test. So inverse Laplace transform of I of s is equal to I of t, and that's equal to 18 times e to the negative 9t times cosine of square root of 19t. See, that square root of 19 comes right back in. Same thing over here. Finally, we have minus 37.17 times e to the negative 9t times the sine of the square root of 19t. So basically, this form right here, when we take the inverse Laplace transform, that goes right into the exponential multiplied by the sinusoid for each section here. Okay? So you guys should be practicing this and making sure that you have these concepts and these methods down on just like automatic. This is not, as I said before, this is not the conceptual part, this is the skill set part. So make sure the skill set is really, really well practiced. Okay? Next thing we're going to come to is actually going through and deriving all of the initial conditions for each case, and then we're actually going to really start getting into basically example problems in which we look at all the cases. Once we actually get through those, we'll be set up to actually do the most generalized form of the schematic transformation into the frequency domain, and we will keep rolling towards test 1. All right, see you next time.